Hello everyone and welcome to the download. These are Tech Talks for the HPCC Systems community by the HPCC Systems community. Thank you for joining us today for episode 27. I am Trish McCall, filling in for the traveling Jessica Lloyd with us today. Please let others know you are listening to this webinar by posting with hashtag HPCC Tech Talks. As always, each speaker will have a Q&A session where we encourage you to submit your questions and we'll answer as many as time allows. Also, we'd like this to be as interactive as possible, so please look for the poll questions at the bottom of the screen and select your answers as you see them pop up. And we'd love to hear your comments on today's topic, so please rate and reply through the feedback mechanism on the screen. And as a reminder, this Tech Talk is being recorded and will be available for playback. And lastly, we are currently looking for speakers for our upcoming episodes, so if you'd like to be in the spotlight, please reach us at techtalks@hpccsystems.com, and we'd love to have you as a featured speaker. So at this time, I'd like to turn things over to Dr. Flavio Villanustre for our community announcements and today's speaker introductions. Flavio?
Thank you very much, Trish, and thank you everyone for listening to this podcast and webinar. There are a number of things that are quite exciting. I want to get directly into the meat of these announcements. First of all, and this is a more common announcement, the latest version of 7.4 is out. 7.4.18 Gold is out now. If you have been thinking of moving to perhaps 7.4 in the future because you're on 7.2 or even worse on 7.0, you should be now considering seriously to move into 7.4.18. We already, of course, went through the original shake-up of capabilities and features. Now 7.4 is stable. It is a good gold version to move to if you are considering it. Certainly, there is plenty of information in our portal if you want to take a look at the Red Book and also the 7.4 series documentation. There is a link on the screen as well. Please take a look at that. There are also, in a slightly different topic, there are a number of blogs that came out, blog posts. There is one which is quite interesting, particularly if you are interested in time series and building predictions based on time series. This one is from one of the community members that have built a number of interesting approaches to doing this type of time series analysis, but with deep learning, using deep sequential learning for traffic prediction and for text classification, where you can see that context, at least context in the past, is important to be able to do a proper prediction in the future. So if you are interested in time series and you want to learn more about how to apply this to text classification, which is a fairly novel type of application for time series, and also traffic prediction, this is a very good read. And another one, which is a good one too, is what's in your data store, and I will leave it there. Just go and take a look. I'll leave you with some curiosity there on what it really means. There are also the latest version of or the latest post of the 5-question series. This one with Luc Pesset, this is going to be available very soon, so just stay tuned. Check once every while. We'll have it available again in the next few days. Now, the most important announcement is we are officially less than 1 month away from our annual Community Day event. This event will happen also in Atlanta. We will be having the same type of structure in the old events, where the day before the Community Day there will be a number of training and learning opportunities, including this hands-on workshop. There will be also a poster competition. If you have already applied for a poster competition, you're probably already working hard to get your poster ready. If you haven't and you are interested in doing it, please do not waste any time. Just send us anything. I'm not sure about the closing deadline for this, but if you have something that is last minute and we need to get it in, we'll figure it out. On the main day, or day 2, we will have all of the general and also breakout sessions. We have changed a little bit the format there. I think it's a better format. I think you'll enjoy it if you attend. So if you have been slacking and postponing and applying or booking your event, please do it right away because it's quickly filling out, and it's again only 1 month away. So no more slacking and just get on it. Other thing that I wanted to mention is that there is as usual, there is a web portal page for the summit. There is of course bundle pricing if you want for both days, and in any case the ticket is inexpensive, and let us know if you have any special cases that we need to consider as well. And if you're a student, of course, you get your 50% student discount. Now, without more preamble, we'll get into the real deal. This is what we have today. We have a great lineup of speakers. We have 4 people that have been involved with the community, some of them for longer than others, like, for example, Russ Whitehead, who's been with us for a long time. I won't say how long it is because it was quite long. The others are repeats. These are 2 students that have been doing their summer internship with us now twice. Those are Farah and Robert Kennedy. And last, but certainly not least, particularly if you look at the topic, we have Vanel, who just joined us for a summer internship. Now, in order of appearance, Vanel will go first. He has developed an analysis on unsupervised anomaly detection methods using HPCC systems. This is quite interesting because anomaly detection is very useful when it comes to fraud detection, behavioral analysis, and others. So I think you will really enjoy that talk, and it's a very good broad coverage, but also with good deep content, technical content. So that's a very, very good talk. That goes first. After him, we will have Farah. As I said before, she has been an intern with us for 2 times now, and she will be working and presenting the work on domain-based common words. And this will be, she did it, or she has done it, we're using high-dimensional representation of text, which is also an interesting approach to finding common words in domain-specific areas. Next, we will have Robert, and you probably know Robert also from last year. He's been always working in deep learning, but in this particular case, it's an interesting take on it, which is running HPCC systems, running the VM on it on Hyper-V. You probably run HP systems on KVM or any of the other VM alternatives, but I'm not sure how many people in the community run HP systems VM on Hyper-V, and if you want to learn more about it, just wait until Robert presents his part. And last but not least, this is an interesting, also interesting topic because Ras will introduce us to the new cryptographic ECL standard library. We did have for a long time a number of routines across along HPCC in ECL, but we didn't truly tackle the problem of encryption and hashing in a comprehensive way. Now Ras has been starting to build a crypto library that will have support, or already has some support for some of the most common ciphers and hashing algorithms, and it will be enriching that library over time. If you have been waiting to get something like this because you didn't want to code these things from scratch or build an embedded function to support some of these things, this is your opportunity. Just wait for a few minutes and listen to Ras present this. And without any more preamble, Vanel, the floor is yours.
All right. Thank you, Flavio, for introducing me. Hi, everyone. So I am Vanel. I am a master's student at Kennesaw State University. And today I will be presenting about developing and assessing unsupervised anomaly detection methods using HPCC systems. So I will start by a quick poll question. So have you ever had to analyze a log file to get insight about an anomaly or a bug? So you can answer either yes or no, and the answers of the poll question will be given at the end of the presentation. So I will start by the project description. So as mentioned earlier, my project as a summer intern was to develop and assess unsupervised anomaly detection methods. So anomaly detection can spread over many domains. So we have intrusion detection, fraud detection with credit cards, and we have log-based anomaly detection. This one is a rare anomaly detection system, but it's the one I've chosen because it is tightly related to my thesis. So having chosen that, our specific project ended up being developed and assessed unsupervised anomaly detection methods for detecting anomalies in a system through log file analysis. So throughout this talk, we're going to discuss about a brief background on log-based anomaly detection. Then I'm going to describe the data set used for this experiment. Then define our target anomalies, and then the methodology used to find those anomalies, and we will conclude. So about log-based anomaly detection. So this picture shows the 4 main steps which most of the works on log-based anomaly detection have been using. So this picture was taken from the paper shown on the PowerPoint below, experience report from Shinli He and al. So in this picture, the first step is log collection, which is basically getting the logs from any device or from a system. So that's the first step. Then the second step is log parsing, because most of the time logs are unstructured. So this second step just aims at giving them some structure to know what's the date, what's the IP address, basically structuring the logs. Then the third step is feature extraction. At this step, we get exactly what we need for anomaly detection. From this step, we get our vectors. And the final step is anomaly detection. So most of the work now with the advent of machine learning deals with anomaly detection using machine learning. So this is most of the works do in terms of log-based anomaly detection. So they only differ in the content of each of those steps. So having said that, I'm going to now describe the data set we use for our experiment. So initially, we wanted to use HPCC systems log files. However, I was working remotely, so it was a bit insecure to send the logs remotely. So we end up choosing a freely available log data set in the name of NASA HTTP Web Server log data set. And it is basically the records of requests made on NASA HTTP web server for the month of July 1995. And this picture shows a sample of the data set. So these are the first 10 records. And we have we have the IP address, we have the date, we have the request made, we have the reply code, and we also have the number of bytes in the reply. So for the whole data set, we had about 2 million records, basically. And when you are given such amount of records to analyze manually to detect some failures or some unusual activity, so this is usually the head you're going to do because you don't know where to start. So we define our target anomalies for this data set. So our target were twofold. So we had first user anomaly and then workflow anomaly. So user anomaly detects users having a significantly different behavior from the majority of users. So an example would be an extremely active user. And then workflow anomaly detects abnormal periods of activity. An example would be a period of low activity, maybe because some servers were down. So these were our target anomalies. So what was our methodology to find those anomalies? So at the heart of our methodology was K-means algorithm. And for this, we used the HPCC systems K-means bundle. And we had three main steps in our approach. The first one was feature extraction. Then the second one was to use k-means clustering. And then the final one was to use the results of k-means clustering to detect our anomalies. Now I'm going to dive into each of the steps for each of our anomalies. So let's start with user anomaly. So our features for user anomaly was, we had 7 features for user anomaly. So the first one was the average request submitted by each user in the first 8 hours. Then the second one was the average request submitted by each user in the next 8 hours. And then the third one in the last 8 hours. Then the fourth feature was the number of active days, which is basically the number of days the user has been active over the month. And then the fifth one was the average unique daily request, which is basically the average number of requests submitted by the user daily, not considering repetition. And then the before last one was the average daily request, but now not considering repetition instead. So, and now the last one was the average daily bytes in reply, which is basically the average size in reply of daily requests for each user. So those were our 7 features for detecting users' anomalies or to differentiate each user. So having our features, now we move to k-means clustering. So we have to cluster each user. And this is a summary of the k-means clustering process. So the main step in k-means clustering was to decide the number of clusters. And to decide the number of clusters, we use 2 main things. The first one is shown on the left. We had a visualization of our 3 main features in a 3D graph. And this is shown on the left. And on the right, we have a plot, which we call the elbow plot, which shows on the y-axis the number of clusters, and on the x-axis instead the number of clusters, and on the y-axis is the error. So using visualizations, we end up deciding on choosing just one cluster for this particular anomaly. And the table below shows the final position of our centroid. So having the final position of our centroid now, we have to use this to detect potential abnormal users. And to detect potential abnormal users, we basically try to find the distances of all the data points or all the users to our centroid. And we did this and got the following graph. On the y-axis, we have each user ID. On the x-axis, instead, we have the user's IDs. And on the y-axis, we have the distance to the centroid. So now we have the distance of each user to the centroid. And using this graph, we set a threshold above which we will consider a user being abnormal. So having set this threshold and applied our filter, we ended up having 20 potential abnormal users, shown in the table in the slide. And then after analyzing our results, we ended up concluding that we were having 2 kinds of abnormal users. So on this table, we have in the center, we have the centroid, and then on the left, on the right, we have each type of abnormal users. So let's start by the left one. So the left one shows, if we go on the row concerning the number of active days, we see that this abnormal user has been active the whole month, which is 28 days. While the centroid tells us that most of the users have been active between 1 and 2 days. So, and also comparing also the number of requests submitted by this user, we ended up concluding that this user represents the very active users over the month. And it would be worthwhile investigating why they have been so active and every day. Now we have our second potential abnormal user on the right, which shows a pretty normal number of active days, in this case 1. But he has a really high number of submitted requests in the second 8 hours of the day, and who knows why. So This is our labeled as a very active user on a particular day within a specific period of time. So this was our result for user anomaly detection. And before moving to workflow anomaly, we're going to get our second poll question for this talk. So on a scale of from 1 to 5, 1 being easy and 5 being hard, how difficult do you think it is to determine the cause of a failure from analyzing a log file? So you have to answer between 1 and 5, and the results of the poll question will be given again at the end of the presentation. So now let's move on to workflow anomaly, and which aims at detecting abnormal periods of activity. So as for the first anomaly, we had to define our features. So here the first step to define our features was to set the period of activity. And for this one, we decided on 1 hour. And this is a parameter. It can vary depending on the system and depending on your needs or depending on the organization. So we decided to choose 1 hour as period of activity. And the second step here was to divide the data set into windows depending on the period of activity chosen. So we divided the data set into hourly windows. Then the final step to get our features was to count the number of occurrences of each request per window. But so on the left, we have the window IDs, and then we have the count of each request in the table. But at this step, we encountered an issue, which is mainly a dimensionality issue, because we were having about 22,432 unique requests, which is making our features to have a dimension of about 20,000. So that was really huge, and we had to find a way to reduce the dimension. So thankfully, most of the work people have thought about it, and most of the researchers have decided to switch from counting requests to counting events. And events are basically log templates. So to understand this, we can treat get image, get file, and get image. So normally each of those requests will be counted individually. But now instead of counting them individually, we get instead their templates, which is get star, and now we count them as a single event. So this is the basic idea in dimensionality reduction. And many researchers have developed systems to move from request to events. And among the many works which have been done on the domain, they have chosen Spell, which is a streaming parser for system events log developed by Mindu and Fei-Fei Li. And it is based on longest common subsequence. We chose this approach simply because it was fast and accurate for our needs. So having chosen Spell and applied it on our data set, we ended up moving from 22,432 unique requests to 3 events, and which were get star, post star, and head star. And the table below shows a sample of our features extracted. So we have the window ID and the count of occurrence of each of the events now instead of each of the requests. So having now our features, we again move to clustering as before for the first anomaly. And we again have on the left, we have the visualization of our features, and on the right, we have the elbow plot. And this time, having these two, we decided to go with 2 clusters this time. And the table below shows the final position of our 2 centroids. And again, to detect each of our anomalies, we plotted the graph of the distance between each member of each cluster to its respective centroid. And we got the following graph. So this is the graph showing the distance between the the data points in the first centroid in the first cluster to the first centroid. And here we decided again on a threshold beyond which the period would be considered abnormal. So this is for the first cluster, and this is for the second cluster. And after applying now our different thresholds, and we got the following potential, we got 11 potential abnormal windows of activity. So we have two tables. On the left, this is the result gotten from cluster 1, and on the right we have the result we got from cluster 2. And after analyzing and comparing that to our clusters, we were able to conclude that on the left we were able to detect the most active windows, and on the right we were able to detect the least active windows. So at the end of our presentation, so we were able to develop and assess two unsupervised anomaly detection methods using K-means clustering. So from a web server log, we detected potential abnormal users as well as potential abnormal periods of activity. So those information are more useful for a system administrator instead of having to read each line of log without knowing where to start and where to stop. So the source code of this experiment, of this project, can be found on GitHub in the link shown on the PowerPoint, as well in the attachment. As future work, we intended to think about finding the root cause of the detected anomalies, because it's good also to say, okay, we found these potential abnormal users, but it will also be more helpful to know why is that user considered a potential abnormal user. And then another future work is to develop an online anomaly detection system, because this one works in batch mode with a monthly record, and it would be more helpful to be able to analyze the logs in real time. And the final way to improve on this work would be to experiment on other types of log files. So thank you for listening to this presentation, and I'll be listening to any question you may have.
Thank you, Vinal. I think this is such an interesting topic given the need for companies today to detect intrusion and fraud. So while you go and review the questions that have come in from the audience, I will share the results of your first poll question. And you had asked, have you ever had to analyze a log file to get insight about an anomaly or bug? And the results show that 100% of the people who took this poll said yes, that they did. So it sounds like we have the right audience here listening in to the talk today. So if you are ready, let's move on to your Q&A. So the first question is, what do you think would be the solution to make log analysis easier?
All right. So there are many problems today in log analysis, and there is a root cause which is related to logging systems, because there is no standard in logging, and many engineers they design their log system the way they like, and sometimes they make errors. So a way to make improvements will be to standardize logging, and also another way to improve on making log analysis easier would be to reduce the workflow as well. So those are the main I would say the main things I think about giving a solution to making log analysis easier.
Okay. And one other question that came in, what are the main challenges of log-based anomaly detection that you see?
Okay, so the biggest challenge in log-based anomaly detection is, as mentioned in the presentation, the company could not send me the log over. So companies are hiding their internal logs, and this makes improving on log analysis a bit complex. So that's one challenge because of security. So another challenge is the explosion of big data, and security analysts can't understand all the logs, all the works, all the logs. They can't really understand everything, and that makes it more complex for them. So those are the main issues for me and the main challenges in log-based anonymization.
Well, thank you for providing that insight. So before we wrap up with Vinal, let's go over the results of your second poll question, which was, and I like these questions, on a scale from 1 to 5, with 1 being easy to 5 as hard, how difficult do you think it is to determine the cause of a failure from analyzing a log file? And from the results, 60% of the listeners said they rated it a 3, so I would say average, challenging, and 40% rated it almost a 4, so almost as hard. So it definitely looks like what you're sharing here will help our users. So thank you again, Vinal, for your insight on this topic and for your contribution of the anomaly methods that you shared with us today.
All right. Thank you, Trish.
Thank you. All right, so at this time, I would like to turn things over to our next speaker, Farah Alshanik from Clemson University, and she'll be presenting her work on a domain-based common words list using high-dimensional representation of text. Welcome, Farah.
Hi, Trish. Thank you for your introduction. Hello, everyone. I am Farah Alshanik. I am a PhD student at Clemson University. And today I'm going to talk about how to extract the domain-based common words using the high-dimensional representation of the text. First of all, let me ask you a quick question. Have you used machine learning to extract important information from a free-form text? And the result of this question will be shared at the end of the presentation. Okay. So today, we are living in the era of big data, which we have a lot of data from various domains. We have, for example, financial, political, industrial, and medical data sets. And in order to find the trends or the insights in the data or to handle these huge data sets, we need to clean the data first. And the text cleaning is a crucial step in any data mining or natural language processing. One of the most important steps in the text cleaning is the stop word removal, or what we call the stop word reduction, which eliminates the words that are noise words, and these words are irrelevant to the content or non-predictive because they carry low information content. So we don't need these words. We need to eliminate them, because when we eliminate them, we will save a huge amount of space in the text indexing. But most of the researchers remove the stop words using a standard stop word list, like the English standard stop word list, the NLTK, for example, that it has the words like the, is, and these words. However, these words are has its own common word, or the stop words, which is domain specific and has no value within this specific domain or the context. So the domain-based words are different from one domain to another. For example, the word protein would be a stop word in a collection describing medical data, but not in a collection describing political issues. So find an automated method to generate a domain-specific common words play a key role in reduce the size of the corpus before applying any machine learning or data mining task. So in our work, we use the text vector bundle, which is the HPCC machine learning bundle that implements the continuous bag of words that represents the text into a numerical data like words, phrases, and sentences, and encodes the meaning of the text. And these features or these vectors can be used as a feature for any machine learning algorithm. The power of the text vectors is appeared by encodes the meaning of the text. where the meaning of a word is closely associated with the distribution of words that surround it in a coherent context. So the continuous bag of words, which is the text vector bundle, represents the text as vector of n dimension, where the vector are coordinates in a space. For example, the 3D vector have 3 points represent coordinates in 3D dimension, and the n-dimensional vector represents a coordinate in n-dimensional space. The text vector are typically between 20 and 1000 dimensional, and the text vector, the continuous bag of words, finds the coordinates for each word that is close to all words with similar meaning and distant from all words with dissimilar meaning. In our methodology or in our work, in order to find the domain-based words, which is the common words for specific domain, we based on the idea that analysis both vector similarity and the multidimensional scaling demonstrate that there is a significant semantic information carried in the vectors. So we built our theory, which says taking the average dimension of the word's embedding to find the centroid of the corpus will allow us to find the words that have a shortest distance from the center to be a candidate domain-based word. Here we can explain our methodology in detail. So first of all, we use the text vector, the continuous bag of words, to produce a numeric vector for each unique token in the corpus. Then we find the centroid of the corpus by averaging the word embedding. And then we use some distance matrices like the Euclidean distance and the cosine similarity to find the distance for each unique token in the corpus and the centroid. Then we sort the distance in ascending order, and here we found that our methodology or our theory is correct because the words that have the shortest distance from the center are the domain-based words. Then we pick n words with the shortest distance to be a domain-based common word. Here also, the steps that we use, we have a corpus, then we tokenize the corpus, meaning only convert the words to lowercase and remove some special character. In this step, we didn't eliminate any stop words like the standard stop words that and this word. Then we apply the text vectors on the corpus and represent each token by 100 dimension vector. Then we find the centroid by averaging the words embedding. Then find the distance between the centroid and the tokens in the corpus, sort the distance in ascending order, and pick a number to be the domain-based word. So as a case study to test our methodology, we use the PubMed dataset. We use this dataset because it provides public information that is provided by the National Library of Medicine. The PubMed dataset containing more than 26 million citations for biomedical literature from Medline Life Science journals and online books. We used around 92,000 abstracts from 2 journals to apply our methodology on it, which is the Journal of Bacteriology and the Biochemical Journal. So here when we apply the text vector on the abstract, so we represent each token, each unique token in the corpus by a vector of 100 dimensions. Then in this picture we can see after finding the centroid, we were able to apply the Euclidean distance and find the distance between the center and each unique token. As you can see that we have the words, this is the 100 words, domain-based words. We can see that we have the words like or, not today, which is the standard stop word. And in this screen, And also, if you can see, we have the word patients. Patients because we are dealing with a medical data set. So yeah, patients is a domain base for this medical data. And here you can see that we have the word cell, treatment, using a group, milligram, level, protein, blood, results, which all of these words are the domain-based words. So in order to test our methodology, we apply the classification before eliminating the domain words and after eliminating them to see if the accuracy improved or not. So we use a random forest classifier before and after eliminating the domain-based words. We pick this classifier because it can handle large number of records and large number of fields and works well using the default parameter. And also, which is very important, it scales well on an HPCC systems cluster of almost any size. So we use the 6 vectors. So we apply the continuous bag of words on the corpus and represent each sentence by a vector of n dimension. Then we use the sentence vector as input to the random forest, and 20% of the data reserved for the testing. Then we convert our data to the form that's used by the machine learning bundle in the HPCC. So we convert the data in a cell-oriented matrix layout, which is known as numeric fields in the machine learning bundle. Then we separate the independent variable and the dependent variable, which we have the abstract and the journal name. As you can see here, the accuracy before eliminating any domain-based words for the random forest was 49x. And after eliminating around 5,000 words, we were able to increase the accuracy by 3%, so it's 52.9. And this table represents the number of words eliminating and the accuracy. So as you can see, by eliminating the domain-based words, the accuracy does not decrease. So it's increased. And also, we build the confusion matrix before and after eliminating the domain-based words. And as you can see, also the precision and the recall for each classes, which is 0 and 1, 0 represents the journal of bacteriology, and the other journal, which is biomedical journal. So the precision also increased. It was 59, and after eliminating around 1,000 words, it was 51.9 for class 0, and it was 48.6 for class 1, and after eliminating 1,000 domain-based words, it was 49.9. And also the recall is enhanced. So from here, we can see that using our methodology increased the accuracy of the classification and enhance the result of the precision and the recall. So also, in order to test our methodology, we apply the topic modeling. The topic modeling identifies which topic in a set of documents. So since we have papers or abstracts from the papers, we use the LDA, which is a topic modeling technique that converts the set of research papers to a set of topics that to discover the hidden semantic structure in a research paper, which allow us to learn the topic representation of papers in a corpus. So here, when we apply the topic modeling before eliminating any word, as you can see in the first topic, here we have 10 topics. And as you can see in the first topic, we have the word cell, human, protein, activity, DNA, expression, and from this topic, we know that this is a medical data. So the word cell or protein would appear a lot in this journals or in this abstract. So we don't know exactly what this topic about. But when we eliminate around 1,000 words, domain-based words, you can see now the first topic, we have these words like oxygen, test, surgery, mice, and maybe this topic now more clear, and maybe it's about making some surgery for the mice. And from here, we can see also eliminating these domain words enhance the result of the topic modeling. And by the end, I want to ask the domain-based words might be useful for your project. And thank you for your listening.
Okay. Thank you, Farah, for sharing your work on this text vectors bundle. It looks like we've got some questions for you to review from the audience. So while you do that, I will share the results from your first poll question. And you had asked, have you used machine learning to extract important information from free-form text? And it looks like we've got a split audience right down the middle. So 50% have used machine learning for this purpose, while 50% have not yet. So if you are ready, we can move on to your Q&A. Okay. Are you ready for some questions there? Okay. And you can just prioritize the ones that you see coming in. All right. The first one is, let's see. Are you aware of any research that has to be done to analyze using the domain-based common words as a feature in classifying text as belonging to a domain? For example, in a corpus that contains articles about baseball, you might expect the word pitcher to be a common word. And any article that has this as a word may have a higher probability of being about baseball.
So in this question, yes, there is a lot of research that done some researchers have done some research about the domain-based words. Some of them use, for example, the document frequency. Some of them use the information content. So why we didn't use these features? For example, the document frequency. It assumes that the term and the vocabulary have the same importance. But by using this domain-based, our methodology, we not care about the frequency of the words, the frequency of the terms. We are concerned about the similarity of these words between these two classes. So from here, we built our methodology by using the high-dimensional representation of the words that represent the importance of the words also in the corpus, not only the frequency as a number of the words.
Interesting. Okay. Thank you. Another question, why do you not use document frequency to eliminate the words that have low and high document frequency?
Yeah, as I said, the document frequency is the bias toward the uniformly distributed words. So it's biased toward this distribution, and it has it assumes that all the terms in the vocabulary have the same importance, which this assumption does not always work because the importance of the term across the collection varies across all the categories.
Okay, thank you. And one other question for you. Explain how we can identify the stop words or the characteristics of the stop words.
Okay, so the stop words are identified by some attributes. It has low discriminating values. Also, it has low information content, and it has high document frequency. These the words that we said it's a stop word in the corpus.
Okay. All right. In the interest of time, let's move on. So thank you, Farah, for answering those questions. Let's go over the results of your second poll question, which was, do you think domain-based words might be useful for your projects? And not surprising, 100% said yes. So I could definitely see how this bundle will help others having similar needs to make their data more accurate and efficient. So thank you so much for your work on this project, Farah.
Thank you.
And Yep, and as a reminder to the audience, FARA is speaking more about this topic on the main agenda during Community Day, so be sure to register and attend, or you also can listen to the live stream. Okay, so let's move right along. Up next, I'd like to welcome Robert Kennedy from another of our long-term collaborators, Florida Atlantic University. He will be sharing an update on expanding HPCC systems' deep neural network capabilities. Robert?
Thank you, Trish, for that introduction. Like you said, my name is Robert Kennedy, PhD student at Florida Atlantic University in Boca Raton. So I'm real close to the Boca Raton office, the LexisNexis Boca Raton office. My presentation is going to cover two main things. The first being HPCC systems virtual machines on Hyper-V, as well as expanding HPC systems deep neural network capabilities, specifically with GPU acceleration. First, I'd like to start with a quick poll. How much experience do you have with deep learning, if any at all? Please answer, and we'll go over this at the end of the presentation. So like I said, this presentation, I'd like to go over my work that was completed over this past summer internship. Really excited to be back for a second year in a row as a summer intern. And a quick shout out to the platform team at Boca for extending me to a desk while I work. Thank you. So the first part of my project, I created a tool that's used to build virtual machine images on various platforms. It's an open source tool. It's called Packer.io. It can be run on Windows, Mac, Linux, OpenBSD, and Solaris. What it does is it will create virtual machine images locally based off of a config file. You can use it to create different images. For instance, a Hyper-V image with HPCC platform fully installed. You can create an AWS image. You can create an Azure image. You can create a VirtualBox image. You can create a Parallels image if you're on a Mac, which would be really great. And there's plenty of other currently, as it stands, there's a Hyper-V, AWS, and VirtualBox runtime. All these images come with the standard HPCC systems platform, but it's very easy to extend this to install custom programs or tweak the version of your HPCC system that's installed. All you have to do is modify the JSON file. Next, I kind of did a case study of how to use this tool. So I used it to create a sort of custom AWS image. Amazon calls them AMIs. It has HPCC systems 7.2.14, I believe, installed. And it also has all the requirements installed to utilize an NVIDIA GPU, which will then be used in the second part of my presentation. In the second part of the presentation is going to be a GPU-enabled deep learning bundle. Both the bundle and the Packer script and tool are on GitHub. The links are displayed here. I think the links are in the presentation window as well. So please definitely go take a look at them, comment, use it, let me know how it works. I'd really love to see people use it. So HPCC systems on Hyper-V. That was the main goal, I guess, for the first part of this. Hyper-V, for those who aren't familiar, is a hypervisor that's used to run a client operating system within Windows 10, similar to VirtualBox, except it comes as part of Windows 10. Unfortunately, VirtualBox and Hyper-V can't run on the same system at the same time, which can be a little problematic. But basically, the Hyper-V images, so you could use a local HPCC node, but running in Hyper-V. And like I said before, this uses a JSON config file, very easily extended, and it's documented in the GitHub repository for easy use. So real quick, why Hyper-V? Well, other than it would be yet another platform supported by HPCC, at least for a development environment. This idea was first presented as an internship project proposed by the company, so you guys obviously saw the importance. And secondly, it was originally thought that using Hyper-V would allow the use of GPUs locally. Unfortunately, it turns out that's not exactly possible due to the way Hyper-V works. But instance, which we'll go over shortly. Even though it's not compatible with, even though Hyper-V is not compatible with GPUs, I thought it was very important to develop this because Hyper-V is a hypervisor that ships standard with Windows. So you don't have to go out and download VirtualBox, which is a whole other thing. But also importantly, if you happen to run Docker Desktop on Windows, that actually runs in a Hyper-V VM. So if you're running VirtualBox, you can't run a Docker Desktop. So if you happen to have Docker Desktop as part of your workflow, you can now have on the same machine at the same time a local node running in Hyper-V, which I think is great. So I use this tool to create a customized image that's running HPCC and is able to use a GPU for accelerated computation. It supports Python 3.6, CUDA 10.0, TensorFlow 1.14, and PyTorch 1.1. Those are at least the ones I use. Oh, and I think I mentioned the specific version of HPCC I used was 7.2.14. These were deployed and compiled and deployed to both AWS and Azure for testing. I feel that AWS has more cutting-edge hardware options at this point. They have the newer graphics cards if you were to use this for accelerating deep learning. However, as we'll go over in the case study, it's not necessary to have the absolute fastest GPU to realize significant performance increases unless you're at the bleeding edge of deep learning research. Even the cheapest and smallest, the K80, you can realize some very, very significant performance increases. Right, so quick overview on deep learning. This is an increasingly dominant subdomain of machine learning, as I'm sure you know. Deep learning architectures, which are basically artificial neural networks characterized by having both a large breadth and a large depth of layers, so very wide and very deep neural networks. These benefit from training on big data. Unfortunately, the size and complexity of the models combined with the size of the training data makes training these neural network models very computationally expensive. One solution is to accelerate the training procedure using large cluster computers, such as a standard HPCC system, but that has its own challenges. In contrast to this, where basically you just add more CPUs to the problem, another solution is to offload the heavy computations of the neural network training process itself directly onto a GPU. This technique can be, if you ever played around with it, it's significantly faster than on even multiple CPUs. And this is even more so for convolutional neural network. So currently HPCC had some common machine learning algorithms and some distributed deep learning runtimes, but they were all limited to CPU for the computations. So that was the main goal for this part, was to leverage a GPU with HPCC, which is, to my knowledge, I think might be the first to do that, at least specifically with neural networks. So what are we actually calculating? So real quick, this is what a neural network looks like in the lower right. Upper right, this is what a neuron looks like. There's a lot of steps, a lot of mathematical operations that have to occur. So the artificial neuron looks a lot like a biological one. Just like the biological one, it accepts inputs from the previous layers, the previous neurons, with an addition of a weight, with a weight that this weight is what is changed during the neural network training process. And as you can see on the image to the right, you start with your input layer, and then it goes down to the next hidden layer, to the next hidden layer, to finally the output layer. And this is a trivial neural network model. So you can imagine when they get very complex, these weights and the required computations grow really, really quickly. And luckily, GPUs can handle these. So where exactly do the GPUs come into play? Well, during the neural network training process, the main parts. There's the forward pass, where the data is fed into the network from the input side, and an error value is calculated based off the input data, and the loss function for each neuron on each layer, and then it's calculated for the next layer, and it's calculated for the next layer, and it's calculated for the next layer for each piece of data. So if you have a training data set of 60,000 images, which is pretty standard, you have to do this, 60,000 times however many epochs you want to do. So it adds up. Second part is the backward pass. Once you pass through all the data and calculate all the error, you have to then propagate it backwards, and you have to calculate the gradient for each one of those arrows, each one of the connections with respect to the error. And you have to do it backwards for each and every one of these pieces of data. So this is really where the computationally expensive part happens. And I won't go into too much detail here just due to time, but it's basically the gradient descent algorithm is what causes it. Okay, so as you might expect, this is not exactly your average HPCC system. Traditionally, a system would have use a bunch of commodity computers connected via standard network protocols, which can be quick, but with respect to deep learning, this is a very large communication bottleneck, partly due to its iterative nature. So a distributed CPU system might not be the best way to go about solving this problem. Real quick, the paradigm in which the training process happens is called data parallelism. Data parallelism is basically what happens is the data is partitioned across multiple nodes, either GPU or CPUs, and a copy of the neural network model is put onto each one of the nodes. The model is then trained on its local subsection of the data until a certain point, and then everybody stops, all the nodes stops, and then the models are aggregated at certain predefined points to basically have all of your nodes working in unison to create a single neural network model. So you can see this is kind of an image of how it would work. So the parameter server, the green squares would be your CPU, and the blue squares would be your GPUs. The connections between them would be your hardware connections, and then the data shards down at the bottom below the squares would be the localized the GPU memory. All of this is happening basically inside of a single machine, which is in contrast to traditional HPCC systems where it's across multiple machines. So that's a nice takeaway. So with this bundle, you can train neural network models on the GPU. You can also do it on the CPU if you so desire, using data that's stored in HPCC. It's sprayed on HPCC in the standard way. This bundle is brand new, still in its infancy, but you are able to build, train, and use a neural network model by using either ECL only or using ECL and Python. So you'd have to write ECL and ECL together, if you want, is you can have fully customized neural network models to train on data housed on HPCC. You can also make predictions, so you can consume, you can use, you can infer with these neural network models also on a data that's housed on HPCC. So you can kind of, from the whole workflow of designing, testing, training, and using in production, a neural network model can be realized with this bundle, all while using a GPU to accelerate the training process, which can take a long time. Can't really go into too much detail here, but I do want to let you know I will be going into this in much more detail with code examples, output examples, and everything at my Community Day presentation coming up in less than a month. But this is what it would output. So in this task, the model is trained to recognize a handwritten digit. In this case, on the left, it's an 8, obviously, and on the right-hand side, you can see an output in ECL Watch, 10 rows, and it's encoded in what's called one-hot encoding. So what one-hot encoding is there's, so for in this example, there's 10 digits, 0 through 9. So there's an array of 10 integers, all of which are 0 except for one of them, and it's a 1, and the index of that 1 indicates the class that the neural network model predicted on. So this is how you would get your usable, actionable data from the neural network model in HPCC, which is great. So a quick poll before I go into my performance evaluation. Approximately what time frame do you see having the need for deep learning, if at all? And we'll go over this answer at the end. Okay, so quick performance evaluation. I did a case study to measure the performance improvements. I trained 5 identical convolutional neural networks, or CNNs, on the MNIST data set, which is handwritten digits, and I did them 10 times each. I did this on CPU alone, 1, 2, 3, and 4 GPUs to show the difference between using a GPU and not using a GPU, and then showing the increase in performance for each additional GPU. I used, the machine I used was using older K80s, and anything newer would only have bigger performance increases. So this is training a CNN on the MNIST data set between a CPU and a GPU. This was a Xeon CPU, so a pretty decent CPU, I guess, versus a K80 GPU, which is fairly outdated at this point. You can see that the total training time for the CPU took 1,108 seconds, and then on just a single GPU, it took 202 seconds. So it's a 5.4-fold times increase for just using one GPU. And this is on a toy model, on a toy data set. The performance increases are even greater on when you have a bigger model and you have bigger data. So this is kind of like, it only gets better from here. This is a comparison between CPUs and GPUs, but also between the number of GPUs, as well as comparing that to the optimal speed up. So when I say optimal, I mean a linear speed up. So if you use twice the GPUs, it should go twice as fast, which it won't, as we know, because of communication bottlenecks. However, you can see the blue and the green line. The green line is the GPU performance, and the blue one is optimal. You can see that it's very close to optimal as you keep adding GPUs, which basically means there's minimal cost for adding an additional GPU, and you do, in fact, you keep increasing the performance as you keep adding the number of GPUs. They get expensive, though. So in conclusion, I created a tool to create some virtual machine images for Hyper-V, AWS, and Azure, VirtualBox. and demonstrate a good use case of using a customized image. I want a brief overview of the GPU Accelerated Deep Learning Bundle. And again, there will be much more detail presented at the breakout session at Community Day. I think I'm rotation 2, theme 1. So please come see me. Here are some links. The presentation is downloadable, so you can go back and look at this later. And before I conclude, I'd like to ask a third poll question. How important do you think it is for HPCC systems to have deep learning capabilities? So, any questions?
Okay. All right. Thank you, Robert. You know, I think deep learning continues to be a popular topic with our community, so I'm glad that you're able to be here and share your work with us. So we do have some questions coming in from the audience. So while you review and prioritize those, I will go in and share the results from your first poll. And the question you had asked was, how much experience do you have with deep learning? And to me, this is always an interesting question to ask, so we can get an understanding of the background of our audience on who's listening. And lo and behold, 60% said that they have no experience but are very interested in deep learning and learning more. And 20% said that they have experience but not in neural networks. And while the other 10% said that there's no experience and not really applicable to their role, and the other 10 said that they are experienced with deep learning. So an interesting mix, but an astounding 60% with no experience, but very interested. All right, so Robert, are you ready for your first question?
Sure.
Okay. All right, so are there specific GPU requirements? And you know, you had already mentioned the ones manufactured by NVIDIA.
Sure. So as of right now, NVIDIA graphics cards, discrete NVIDIA graphics cards are the only ones supported. You have to have meaning you can't have a GPU on a CPU, which is quite common now. You have to have dedicated graphics cards. And that's kind of mainly because NVIDIA saw the need for this type of, they actually created a whole new API and programming language to access the GPU. They saw the need for that way before everybody else. So their tools that are used are much more robust and pretty much exclusively used, which is kind of amazing.
Yep. Okay, well, thank you for the insight on that one. And your next question, are there any downsides to using a GPU for training a neural network besides hardware costs?
Not really. You know, obviously the GPUs are expensive, but an older GPU still increases the performance by a huge amount, and they're getting cheaper. You can pick them up used sometimes. But no, there's typically no downside to using GPUs. I guess if you had too small of a graphics card memory and too big of a data set, you'd spend too much time transferring data between disk to graphics card memory. So I guess it would really depend on your specific use case, but typically not really. They're almost always faster.
Okay. All right, well, thank you for providing insight there. All right, so in the interest of time, let's just go over the results from your last two polls. And midway through, you had asked approximately what time frame do you see having the need for deep learning? And 66% said within the next 6 to 12 months, while the rest, the remaining 33%, said they need this immediately, that they're either currently using or about to start. So that's interesting, timely there, I would say. And your final poll was, how important do you think it is for HPCC systems to have deep learning capabilities? And the results show 100% said that they think it's very important. So obviously, based on these results, it seems the community will definitely benefit from your bundle. So thank you so much for contributing that.
Oh, thank you. I'm glad I'm
And,
not the only one that thinks it's important.
Yeah, absolutely. And before we end with Robert, like he mentioned earlier, I want to remind everyone that he is also speaking at Community Day, and he'll have a breakout session to dive deeper into this topic. So again, mark your calendars and be sure to register and listen to the live stream of his talk. All right, well, thank you, Robert. Okay, so we now come to our final speaker for today. He's one of our own. He's a colleague from the HPCC Systems platform team. And my good friend, Russ Whitehead, he'll be giving an overview on the new cryptographic ECL standard library. Russ, over to you.
Well, thanks for that introduction, Trish. Thanks for the opportunity to come here and tell you about the new cryptographic library that I just finished implementing. I'm going to start out with a poll question just to gauge the audience's familiarity with cryptography. How familiar are you with OpenSSL, encryption, and digital signatures? It's a scalar answer from very experienced to no experience at all. And you know the drill. We'll see the results at the end. So to introduce you to this new cryptographic plugin library, there's been some requests from internal HPCC users and from an external banking customer for a method to encrypt column level, not necessarily an entire data set, but to further protect the data that is considered sensitive. So I was tasked with this mission and created it with, I give you the JIRA number here in case anyone wants to go look at the source code and evaluate my work. But what it does is this is a library that lets you do various cryptographic functions and transformations on data, which I'm going to talk about in just a minute. But I wanted to let you know that it is available in current builds, HPCC Systems version 7.4.16, which I'll show you the link at the end of the presentation where you can download it and give it a spin yourself. This new function is part of the ECL standard library, so it's available to anyone using the ECL IDE, the command line ECL, the ECL Watch Playground, or directly interacting with WS Work units. Okay. So before I jump into the library itself, I just wanted to familiarize you with the types of cryptographic functions that are out there, and then I'm going to dig deeper into what I enable with this new library. At the highest level, there's hashing functions, which is used to verify data. It's not used to encrypt data. As a matter of fact, you typically use a hash with plain text, like let's say an email. What hash does is it transforms a variable length set of data to a fixed size. For instance, one algorithm I'll show you, it always ends up being a 64-character hash. And it's important to note that a hash cannot be reverse engineered back to the original data. And it's also guaranteed that that you won't have a hash collision. If you can't have two different sets of data that compute back to the same hash. And finally, it's fast, and that's going to be important. I'm going to tell you why later on. The next thing is encryption, and there's two different types of encryption. There's symmetric and asymmetric, and I want to go over the difference of those with you. Symmetric encryption uses the same shared key. So the sender of the encryptor of the data and the receiver that decrypts the data, they have to have the same key. If you have it, it's a very fast algorithm, and using symmetric algorithms, you can support the encryption of blocks of data or streaming data. Okay. The alternative to symmetric is asymmetric, and you've certainly all heard of public key algorithms or public key infrastructure, and what those are mathematically associated key files. The public key, as its name implies, is widely distributed, and that's used to encrypt data, and the private key is held typically by just one or two entities, and that's the only that it's closely held and is used to decrypt the data. It's also used to create digital signatures, which is just another form of a hash, which I'll go over that shortly. But just want to point out that this is a relatively slow algorithm. So now we're going to dive into the details of how what we've implemented and the support that we have. So what is a cryptographic hash? It's a mathematical algorithm. It maps a variable length of data to a small fixed size bit string. As I mentioned earlier, it cannot be reversed or inverted. And the way it works is the sender of the data will compute a hash, send let's say it's an email, a plain text email, and the hash, and the receiver will use the same algorithm to compute a hash and compare the two. And if they match, then you know the data has not been tampered with and it's trusted. Okay. So what we have here is is a sample of ECL actually using the new cryptographic library. At the top you'll see, and this is a common pattern you'll see throughout the library, is there's a method you can call supported hash algorithms that's going to return to you the names in a set of strings of all the algorithms that we support. At this time, the 5 there are listed that we support. These are trusted algorithms developed by the United States National Security Agency. Probably SHA-256 is the most common one that I've in my experience that I've seen. So if you want to look at the ECL that follows, this is a simple thing. You import the standard library as always. The next line defines a hashing module called hashing, and the attribute you pass it is the name of the algorithm, which in this case is SHA-256, and what you get is the reference to the hashing module. So the next 2 lines is actually using that module to compute hashes. In this case it's text strings, but you'll notice that it's cast to data, and that's because the hash I allow you to pass data, which means you can do strings, you can do binary data, you can do whatever you want, and what it returns to you is a data type, a hash, and that's what you send out, and in this case it just outputs it to the work unit. But the point here is that we strove to come up with a simple interface. If you've ever programmed using OpenSSL, it's very complex and very intimidating, and so what we wanted to expose to the ECL users is something that's quick and simple and makes sense, and this is an example of that, I hope. The next thing I want to talk about is symmetric encryption, which, as I alluded to earlier, and if you look at the diagram, uses the same key. The sender and the receiver each has the same key. The sender encrypts the data using that key, sends the data, and the receiver uses that same key to decrypt the data. The key management is a topic here of interest. It's important that the key is protected, because anyone who has the key then can intercept the data, modify it, decrypt it, do all sorts of bad things. So that's one of the common topics in encryption, is how do you manage the safety of the key, and that's something I can't really tell you how to do. There's all sorts of different ways out there which you can use, but I want to show you now an example of using it. It looks very similar to what you saw before. There's a method you can call to get the supported algorithms, and in this case we support 3, AES 128, 192, and 256. The difference between all these algorithms, as you might guess, is the speed at which they compute the encrypted data, and also the complexity of how hard it is to crack it. So as before, you import your standard library, and then you define a symmetric encryption module. The attributes that you're going to pass it are the algorithm name, which was returned from the call above, and a passphrase. And each algorithm has some restrictions on the passphrase, that the length of it, the complexity of it, and that's not something we control. That's up to the control of the algorithm. So you have to look that up to understand the size of each. But anyway, once you've created this encryption module, then you just call the encrypt method on it to encrypt data. As before, the type that it accepts is a data, not just a string. So you can encrypt anything, and it returns a data object with the encrypted data in it. And then if you'll see in this example, I just immediately pass that encrypted data to the decrypt method and assert that they're the same. And again, the interface, we strove to make it as simple as possible, not intimidating to the ECL user, and it's that simple. Okay. Now I want to talk about asymmetric encryption, and as I alluded to earlier, this uses public and private key pairs. As you'll see in the graphic, the encryptor uses a public key to encrypt the data and send it over the wire. The receiver, which holds the private key, uses it to decrypt the data back into plain text or to the data, whatever format it was in originally. This is known as public key cryptography. You've probably seen PKI, which is public key infrastructure. There's numerous three-letter acronyms floating around. But as I said, it has asymmetric pairs of keys to encrypt and decrypt. You can generate these keys yourself. There's OpenSSL utilities, command line utilities, where you can generate them. Or you can send a request to a certificate authority to send a more secure and verifiable public and private keys. And as I said, the public key can be widely distributed to anyone. It's used to encrypt the data, and the private key you want to keep tightly held because it's the one who can decrypt the secrets. Of interest here is that it's slower than symmetric encryption and decryption. So of note, if you've ever used SSL or transport layer security, the way it works is it uses public and private keys. So once they use those public and private keys, which like I said is slower, to establish a secure channel, then what they do is dynamically generate their own symmetric key and exchange that over the channel, and then further communications on that channel uses symmetric, which is the faster. That's just an interesting thing I found while I was researching this. So again, this should be starting to look familiar to you. There's a ECL call to make that returns a set of strings of all the supported public key algorithms. And at this point, RSA is the only one that we support. And the next two lines, what I want to demonstrate here is that there's two ways to define the module to do public key encryption. You'll see the difference is, one, you can pass it key file names for the public and private key. This is a file system specification that will have to exist on the nodes, and we'll go out and open the file, read it in, and use it to perform the public key functions. The other one takes the keys as a buffer, so your ECL could stream it in from some other source and then pass it on to create these modules, which then use it to perform the functions. So the ECL example that you see below, as always, import your standard library and define your public key encryptor module. The attributes that you pass to it are the algorithm name, of course, and in this case I took the public and private key buffers and a passphrase. And that defines the module that you then subsequently call iteratively or whatever your needs are to encrypt the data. And again, all you pass is the data. And if it's string, you have to cast it to data. And in this example, I encrypt it, then I immediately decrypt it, and then just output the decrypted string. And that's it. It's easy to use as that. Finally, I want to talk about digital signatures. A digital signature is just a hash, which we talked about before. In this case, though, it's computed with public and private keys. Again, the intent of a hash is meant to verify that your data has not been tampered with or massaged, but instead of using the simple algorithms as before, this is more secure in that it uses public and private keys. It is going to be slower than a hash, but it's more secure. And again, the sender of the data will compute that signature, send the signature with the plain text data, and the receiver will recompute the signature with that plain text data and then compare the two signatures, ensuring that they're the same. And of course, if the hash doesn't match, or the signature doesn't match, then you know the data's been tampered with and it's unreliable. So for my final ECL example, I show you again, you saw this before, the supported public key algorithms. As I said, the digital signatures and public key encryption and decryption both use the same module. So again, as before, you have two different ways of defining the module, from a file spec or from a buffer. And what you'll see in my example here is I create the module as before. And to sign the data, you just pass the data. In this case, it says, please grant Bob 1 Bitcoin. And then to verify the signature, you pass that signature and the original plain text, which in this case has been tampered with. It says, grant Bob 5 Bitcoins. So the assertion below says that it should have returned false. And that's all a digital signature is. So in conclusion, this library is in its infancy. It is available now, and I hope you guys will get your hands on it and start to use it and give me some feedback. You can download it from the HPCC systems build 7.16 and newer from the link below. The goal over time is to add new algorithms, add new cryptographic features, functions, enhancements. And I do want to mention the documentation will be available in the library user's guide, and also I believe the ECL IDE. But give it a shout, give it a try, and reach out to me directly with comments, or you can open a JIRA or post comments on the HPCC systems forum, whatever method you prefer. And finally, if you want to talk about it or any other platform topic, if you're going to be at the HPCC systems October 16th, the platform team will be hosting what's called a Platform Expert Lab, which there'll be details given at the conference, but we'll be at table 550, and I encourage you to come by and just meet us. Tell us what you think, give us some ideas, ask any questions, or talk about any problems you have, whatever. Love to meet you all. And real quick, I just wanted to acknowledge that I didn't do this all by myself. Dan Camper helped me with the ECL interface design, which is an area that I'm not that familiar with. We came up with a really clean interface. Jim DeFabia, he knows everything about the HPCC systems platform. He helped me with integrating in the standard library, and he came up with some really good code samples, which I hope you look at in the documentation. It shows you how to stream in public and private keys and all sorts of other things. And as always, Gavin Halliday and Jake Smith, who reviewed my code, made sure I kept it clean, gave me ideas on how to optimize it, and just basically help me make it a better library. So finally, I want to have follow-up poll questions. do you feel it's useful to encrypt sensitive data columns even when the data set itself is encrypted? And of course, we'll go over that at the end. So, Tricia, let me hand it back to you.
Okay. Thanks, Russ. You know, I think it's great to have this security feature now available to the community to leverage. So there are some questions waiting for you as well. So while you take time to review and prioritize those, let me go over your first poll results. And the question was, how familiar are you with OpenSSL, encryption, and digital signatures? And 75% have some exposure, so while 25% have not. So again, a suitable topic, I think, for this audience. So let's go on to the questions. Are you ready?
Yes.
All righty. Got quite a few in here. So first up, how do you provide key file contents and passphrases without encoding them in ECL?
So yeah, this is really an ECL question. Obviously, you don't want to hard code private key files and passwords in your ECL. So you would need some kind of external store. There's different ways that you can do it, but some type of library where you can externalize these things and read them in through ECL. And I know I'm being a little vague, but if you look at the documentation that's coming out, we show one or more ways of doing that without having to expose it in ECL code. You theoretically could put a public key file in your ECL code, but that's, you know, over time they expire as well, so it would not be a good idea. So as I alluded to earlier, key management is a hot topic, and you know, that would take some time to think something like that through.
Yep. Okay. All right. Next up, how would you decide which of the supported cryptographic algorithms to use?
So each one has its own characteristics. Generally, the more secure they are, the slower they're going to be. So depending on the sensitivity of the data, and you'd have to do some modeling to see, you know, the performance hits that you take by selecting one over another. But you want to choose the one that's going to most be appropriate for the sensitivity of the data that you're protecting.
Mm-hmm. Yeah, that makes sense. And then how would a cryptographic hash be useful in an ECL data set?
So to me, what I see is, like I said, a hash is always going to be a fixed size. So if you have a large piece of data that you're indexing over, what you could do is create hashes of that data. And because a hash is guaranteed to be unique without collision, you could use the hash as your search key. So when you want to search for something, you can compute a hash on the fly and then look up using the hash or a digital signature.
Yep. Okay. Thank you. And then I think the examples that you gave in your presentation with the ECL code will be very, very helpful. Okay. And then one last. Yeah. Go ahead.
I was just going to say we tried to make the interface as easy as possible because it can be very intimidating if you're using the native libraries.
Well, I think in general, at least to me, security is an intimidating topic as it is. So I'll take all the help that you want to throw our way. One last question before we wrap things up, Russ. Is there a simple supported way to support hashing particular fields in a data set, or do I need to write a project with a transform to perform that hashtag?
This one is beyond me. I would have to defer to some of our ECL experts, but I'm certain there is a way to do it. I could ask someone else and get an answer for you.
Okay, that'll be good, and we can always provide that afterwards. So thank you for answering those questions, Russ. And your last poll to the audience was, Do you feel it is useful to encrypt sensitive data columns even when the data set is encrypted? And the results were, go back to that. Everybody's waiting. Drum roll. 100% said yes, so not obvious. So that is a good to see that our audience thinks an extra layer of security is always useful to have. So thanks again, Russ. And as you stated earlier, you know, you're also taking part in Community Day. Russ will be managing the Platform Experts Lab in our first ever interactive expo. So this will be an area where attendees can engage in demos, ask questions, and seek advice and tips from our HPCC systems experts who will be there on site. So yet another reason that you don't want to miss this event. So as we wrap things up, thank you again to all of our speakers today and for Flavio for all your fabulous contributions to our HPCC systems community. And as a reminder, we're always looking for new topics and presenters. So if you have a success story or a new bundle or tool that you would like to share with the community, we'd love to have you as a speaker in a future episode. So please reach out to us at techtalks@hpccsystems.com. And just to remind you, a recorded version of this episode will be available for replay later today. And you can find that on the event page as well as our Tech Talk Wiki. And that's located on our website, hpcsystems.com, under the Community Tech Talk menu. And then lastly, once again, I want to remind our listeners that next month we are taking episode 28 of the Tech Talks on the road. This will be happening live during our annual Community Day event, October 16th. And as Flavio mentioned in the announcements, registration is still open for a couple more weeks. So check the event page for more details, and I hope you can join us. So thank you again to our audience for so long.